All right, so today we're looking at 5.3, independence and the multiplication rule. If two events are independent, well, two events are independent if the occurrence of one event does not affect the other. Then events are dependent if the occurrence of one event does affect the other. So talking about the difference between independence and dependence. Okay, so next exercise, we want to determine whether we have two independent events or not. So the first one, suppose you flip a coin and roll a die. Are the events obtain a head and roll a 5 independent? I wonder if I can squeeze that in there. All right, so you flip a coin and roll a die. Are the events obtain a head and roll a 5 independent? And the answer is yes, they are independent. One thing has nothing to do with the other. Flipping a coin has nothing to do with rolling a die. They don't affect each other in any way, so they are considered independent. Next one, are the events earned a bachelor's degree and earned more than $100,000 per year independent? No, they're not independent because earning a bachelor's degree increases your chance of earning $100,000. Doesn't guarantee it, of course, but it increases your chance of earning $100,000 or more. All right. Okay, scroll all the way up. All right. So the multiplication rule for independent events. So once again, these are for independent events, the events that we know have nothing, don't depend on each other, or one has nothing to do with the other. the probability of E and F occurring, you will multiply the probability E times the probability of F. I remember last class we were looking at the probability of E or F occurring. This time we're looking at the probability of E and F occurring. All right, so here we have in the game roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot number 17 2 times in a row? I'll give you a chance to write it. All right, so first thing you want to do is establish, are these events independent or not? So these events are independent. The occurrence of rolling 17 does not affect the occurrence of rolling 17 again. All right, so we have to find the probability of rolling 17. So we see that our sample space, we did this all last class, that class before, looking at our sample space, we have 38 numbers. Talking about 0, 00, and then 1 through 36. 17 is just one of those numbers, and it doesn't appear more than once. So it's just one as far as the number of our event is concerned. So you have 1 over 38 as our probability. All right. So we're talking about rolling 17 twice. So rolling 17 and then 17 again. And so you're talking about 1 over 38 times 1 over 38. And those are your two different ways of representing that probability. So of course my math lab will let you know if they want a decimal or a fraction. All right, questions on that one? Okay. The probability that a randomly selected 24-year-old male, let me see if I can get this in here, will survive the year is 0.9986. According to the National Vital Statistics Report. A, what is the probability that 3 randomly selected 24-year-old males will survive the year? And then B, what is the probability that 20 randomly selected 24-year-old males will survive the year? All right. So first thing you want to establish, are the events independent? In other words, does one 24-year-old has anything to do with another 24-year-old surviving throughout the year? So the answer is no. That means they are independent. They have nothing to do with each other. All right. The probability that a 24-year-old male will survive throughout the year is 0.9986. Remember, they gave us that probability. And then here, talking about the probability that all three randomly selected 24-year-old males survive, is just taking that 0.9986 and multiplying it to each other 3 times. Over here, just showing people how they could put it in their calculator using that symbol. So the probability would be 0.9958. All right. So the next one, you want to find the probability of 20 surviving. So that's wherein this symbolism comes into play more so versus in that one. The first one, we could multiply 3 times itself without a problem. But you don't want to get into the thought process to have to do that without using symbolism and the exponents and everything, because you don't want to have to multiply this number to itself 20 times in the calculator. You want to be able to just type this in the calculator and move on, because it's easy to miss one. So make sure you know how to use your calculator. If you have any issues, always feel free to ask. Once again, if you don't have, let me see, whether it be a symbol like this on your calculator so that you can put a number in your exponent, or you may have something like this, x and then a y is your exponent, or like I said, if you have this symbol, that will help you to raise it to 20th power as well. So those are different things you will be looking for in order to be able to multiply something times itself 20 times. All right. Or another one is when they have the box here and a box like that. So they'll let you put a number down here and right here. So it just depends on the type of calculator that you have. All right, so the next one, compute the probability that at least one male out of 1,000 24-year-olds will die during the course of the year if the probability that a randomly selected 24-year-old male survives the year is 9986. So leaning on the same thing, same information that we had in the last example. Give you a chance to write it. All right, so we want to keep the probability that at least one male out of that 1,000 24-year-olds will die. Now, the probability that we have is a probability that the 24-year-old male will survive. So we're going to use the complement rule. So if you're talking about at least one dies out of the 1,000, remember 1,000 with a 0.9986 raised to the 1,000 power is a probability that all of them will live. So now if we want to know the probability of at least one of them dying, so that means we get considering more as well, you would take that probability that all of them live, that's 0.9986 raised to 1,000, and subtract that from 1. And that'll give us 0.7536. All right. Questions on that? That's it for 5.3. Any questions on that before we get into 5.4? All right. All right, so 5.4, conditional probability and the general multiplication rule. All right, conditional probability notation is as follows. You have P with this line in between E. That's the probability that F occurs given that E has already occurred. So this is a conditional probability. These are dependent events. Remember, independent events has nothing to do with each other and nothing to do with the probability of another one occurring. Here we have dependent events. F is going to occur given that E has already occurred. So the fact that E has occurred affects the probability that F will occur. So, and also notice the notation, F comes first, then E in your notation. So that means the probability that F will occur given that E has already occurred. So here we have the way that we can calculate it. You will take the probability of E and F and place it over the probability of E. Or if you have the number of E and F, place that over the number of E. All right, so let's try this out. Where's this? Okay. So we have this chart here for our first example. So this is the marital status of males and females or old, females 15 years or older in the US. And it is in millions. So you have never married, married, widowed, divorced, separated on the left. Then on the top, you see males, females, and then our totals. All right. So let's use the table to answer the following questions. Compute the probability that a randomly selected individual has never married, given the individual is male. Then we're going to compute the probability that a randomly selected individual is male, given the individual is never married. All right. So I'm going to call N for never married, and then M for male. So we look at the setup of the first one. Let's go back to A. We want to compute the probability that a randomly selected individual has never married, N, given the individual is male. So see, we have N, and you can look at that slash as the word given. So should I write that better? So never married, given that the individual is male. So I need to look up the number for never married and male, and then look up the number for all the males. So never married and male is right here. And then the total number of males is right here. All right. So that's why we have 41.6 over 122.5. And convert that to a decimal. My math lab will let you know how many decimal places they want. I think in the book they gave just 2 decimal places. So. All right. Any problems with that? All right. So same type of deal. And for B, but this time they want to know what's the probability that randomly select a person is male, given that they were never married. All right. So once again, I call M male, and then N never married. So I want to know the number of male and never married, and then the total number of those that are never married. So go back to my chart. So we already know that males and never married is 41.6. But then the total number of never married. I was like, hold on, which one are we looking for again? Yeah, but total number of never married is 78.5. That's over there. So you should have 41.6 over the 78.5. Divide those out, that's 0.53. All right, questions. All right. Suppose that 12.7% of all births are preterm. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? And then, is this unusual? All right. So I decided to call W, the event W, weighs 8 pounds, 13 ounces or more, and then P preterm. So we shorten up. Now we describe and deal with the problem. Now the probability of getting preterm, if it is preterm, is 12.7%. So I'll convert it to a decimal and then put my percent here. Preterm are preterm and weighing 8 pounds, 13 ounces or more, 0.22%. So carry your decimal 2 spots to the left, just like we did with 12.7%. That's 0.0022. So we wanted to know what was the probability of a randomly selected baby weighing 8 pounds, 13 ounces or more, given that the baby is preterm. So here's how we'll do that, just like before. So the probability of having a preterm and it weighing 13 ounces or more, 8 pounds, 13 ounces or more, 0.0022. Place that over. Probability of getting a preterm baby is going to be 0.0173. If you had to convert that to a decimal, it's 1.73%. All right. So now, is it unusual? Remember, that was the last question. And the answer is yes, because the probability is less than 0.05, in other words, 5%. Remember, we talked about something being unusual before, and our marker was 5%, being less than 5%. All right. Any questions? All right. So the general multiplication rule is that you multiply, if you want to know the probability of E and F occurring, you'll multiply probability of E times the probability of F given that E has already occurred. Remember before when we were looking at the multiplication rule, we would just multiply the two probabilities together because we were dealing with independent events. Now we have dependent events. So when you have dependent events, you have to give an account for the probability of F given that E has already occurred. So E occurs here, then this is the probability of F given that E has already occurred. All right. So look at this first one. The probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket given that he or she is pulled over is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? Oh, give you a chance to write. All right. So the probability that this person gets a ticket is T. Probability the person get pulled over is going to be P for us. So we already saw that the probability of getting pulled over is 0.8. And the probability of getting a ticket given that you were pulled over is going to be 0.9. So the probability of P and T occurring is going to be the probability that you get pulled over, and then the probability of getting a ticket given that you were pulled over. So that's 0.8 times 0.9, which is 0.72. All right, any questions? All right. In a study to determine whether preferences for self are more or less prevalent than preferences for others, researchers asked individuals to identify the person who is most valuable and likable to you, or your favorite other. Of the 1,519 individuals surveyed, 42 had chosen themselves. I'll give you a chance to write. All right. So A, suppose we randomly select one out of 1,519 individuals. What is the probability that he or she had chosen self as a favorite other? All right. So we know the number of our sample space is 1,519. And we have 42 that chose self. So we do 42 over that 1519 to calculate our probability. All right, so the next one, if two individuals from this group are randomly selected, what is the probability that both chose self? So we already found the probability that one chose self. That's 42 over that 1519. Probability that both chose self. And so as far as the notation, we're just looking at the first one choosing self and then the second one choosing self. So now the first one is that 42 over 1519. But now the second one, the probability that the second chose self, given that the first chose self, we have to consider the fact that when you chose somebody or pick somebody out of the group of 1519, the one is gone. And so that's why we have 41 over that 1518, because that's how many is left. So you chose one out of the 1519, and one of those people were out of that 42 that chose self. So that means there's only 41 people left that chose self, and there's 1,518 people left in total. So that's why each one of those categories go down in one. So one was taken out in each case. Then you multiply those two together, whether you want to multiply in a fractional form or decimal. My math lab will let you know how they want that answer and how many decimal places they want you to round to. Really didn't, someone must have asked a question about the part in green. You really didn't have to do that. You really could multiply them in fractional form in your calculator and still got this answer right here. All right, questions, any questions? And the next one might be the last one. Yep, last one like that. So compute the probability of randomly selecting two individuals from this group who selected self, assuming independence. So if you're talking about independence, remember the events have nothing to do with each other as far as one happening and the other one happening. So once again, we're looking at the probability the first one you chose chooses self, and the second one you chose chooses self. So if they're independent of each other, that means the probability of 42 over 1519 would be the same for both cases. Remember the fact that the first one, you chose the first one, has nothing to do with the fact that you chose the second one. So the key phrase in here, the key word in here is the fact that we're assuming independence. And so that'd be 42 over the 1519 times 42 over the 1519. Multiply those together, and that'll be the answer. All right, questions, any questions? All right. So, that's it for 5.4, and that means that's it for chapter 5 completely. So you want to try this stuff out. See if you get stuck. You know, every day is opportunity for questions. So you can ask those questions in class or shoot me an email. Did anybody have any questions before we close today? All right. So you guys have a good one. Be safe. And I will see you guys on Wednesday.